Welcome to Finite Element lecture series by Civil Thinking, and in this class we are going to solve a 1D problem. Okay, and in this class we are going to see a bar or a rod with axial forces, right? Because as you can see, these are the axial forces and we have this rod. Okay, so before I move on, I suggest you to please watch my video lectures on finite element method analysis one by one as in the playlist, so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now coming to the today's class, now as you can see this, you can see the lengths are more than the cross section. Okay, so you might have known from my previous classes, because when length is more than the cross section dimensions, okay, and in this case what we use 1D meshing. Okay, so in this case we have the one dimension is more than the other two dimensions. Okay, so for example, if this has a square or a rectangular cross section, and then you can see this is small. Okay, this is one, for example, this is y component, this is z component, and let us say the length is x component. Okay, so here you can see the x is 50 plus 50 is 100 mm, and this is more than x is more than y and z, so we will use 1D meshing. Okay, so let us begin. So let me solve this problem in steps. So remember what we have to find. We have to find in this problem what we have to find. We have to find the unknown displacements, okay, and unknown forces. Okay, we have to find. Okay, so let us solve this problem. Solution. So the step one is what? Always meshing. Okay, so we have to mesh the body, given body discretization. Okay, and we also have to write what? Meshing with forces and displacements. Okay, so as I have told you before, we will use 1D meshing. So 1D meshing, what we do, we use a line, right? A line. Okay, so let me draw a line here. Okay, so then we have to draw the nodes. Okay, so but for the nodes we have thumb rules. Okay, number of nodes. Okay, so when you have to decide about the number of nodes, you have to remember two things. Okay, or rather three points. Okay, so you have to draw the nodes at ends. You have to draw the nodes when there is change in cross section. Okay, cross section area. Okay, then you have to draw the nodes also at what? Change in Young's modulus. Okay, we also have to draw the nodes at what? At supports. Okay, now this is the free end and this is also the free end. Okay, so we will draw nodes here. Okay, and here we have a change in cross section, and we will also draw a node here. Okay, so if now for this the E is constant, so for this the E is constant. Okay, so if there was E was for this was something different and for this part was something different, I would have also drawn the node here. Okay, but here the E is uniform for this. Okay, so also for example, if there was a force here, and then I would have also needed to draw the node here. Okay, but we don't have any force here. Okay, so this is our free body diagram kind of. Okay, meshed body. Then we will draw what? We will draw the forces and displacements. Okay, let me first number the nodes. This is node 1, 2 and 3. How many elements do we have? We have 2 elements. Okay, one element is between 1 and 2, and between 2 and 3 we have second element. Okay, so we only have 2 elements. Okay, so now let me draw the what we call them as forces. Let us say the force here is F1, the force here is F2, and the force here is F3. Okay, now let us say the nodal displacements here at this node, the nodal displacement is U1, the nodal displacement here is U2, and here the nodal displacement is U3. Okay, so we have three nodes. At node 1 we have the force of F1 and the nodal displacement of U1. At node 2 we have a force of F2 and nodal displacement U2, and at node 3 we have a force of F3 and nodal displacement of U3. Okay, so we have drawn the meshed body along with all the forces and the nodal displacements. Okay, so remember, you have to always draw these nodal displacement. Although this is a fixed support, there is no displacement here, but still you write this U1 here. Okay, because we have to write the stiffness matrix equation, so we have to fill up the things. So we will write the U1, U2 and U3 everything here, and F1, F2, F3, and then when U1 for example is 0 here, then we will put in the second step U1 is 0 when we apply the end conditions. Okay, so you have to write this independent of where the force exists or where the force does not exist. Independent of force, independent of support conditions, you have to always do like this. Okay, so we have done this step 1. Okay, so now let us go to the step 2. Okay, step number 2 is what? We have to draw the what? We have to write stiffness equation of each element. Okay, each element. Then what we have to do? Then we have to find the degree of freedom of whole body. Okay, whole body means all elements. Okay, and after this we have to formulate the global stiffness equation. Okay, global stiffness equation. Okay, so first we write the simple thing is, first what we do, we write the stiffness matrix of each element and then we add. Okay, stiffness matrix of this element plus stiffness matrix of this element, it will give you the global stiffness matrix with this global stiffness matrix. Okay, so we have to write the what? Global stiffness matrix of each. Okay, it is not equation, it is matrix. Okay, matrix, it is stiffness matrix of each element. Okay, then we add them and we get global. Okay, so the stiffness matrix of each element. Now in my previous classes, I have already told you, you can also watch that lecture, that the stiffness of each element in 1D meshing, the stiffness matrix for each element is K equal to AE divided by L, 1 minus 1 1 and minus 1 and 1. Okay, so we will use this equation to find the stiffness matrix of each each element. So here it is our K1, so it is going to be A1 E1 L1. Okay, then we will find K2, so it is going to be K2 is A2 E2 by L2, and then we are going to do what? We will find the global stiffness matrix, which is sum of the stiffness matrix of each element. Okay, so we only have two elements, so the sum, it will give you the global stiffness matrix. Okay, so for this let us put the values. Now AE by L. Okay, here it is AE divided by L. A is 150, E is 200 and it is 50. Okay, these are in mm and it is in gigapascal, so it is 150 250. Okay, it is 150 200 divided by 50. Okay, it is in mm square, it is in gigapascal and it is in mm. Okay, so let me use a calculator to find the values. 150 times 200 divided by 50. Okay, so it is 600. Okay, now here it is gigapascal and these are in lengths. Okay, if I convert this into megapascal, because megapascal is Newton per millimeter square, so then the dimensions will be millimeter and millimeter. Okay, so for the uniformity of units I will convert gigapascal into megapascal. Okay, now giga is 10 to power 9 and mega is 10 to power 6. Okay, so what is the difference in the powers? 9 minus 6 is 3. Okay, so 10 to power 3 is the difference, so it is 600 into 10 to power 3 megapascal. Okay, megapascal. Now mm square will go mm, and then we have this, right? 1 minus 1 minus 1 1. Okay, then for this A2 E2 by L2. Okay, what is it? A2 is 170 by 50. Okay, 170 by 50. Okay, so I will apply the same rule here. 170 by 50, it is in mm square, it is gigapascal, it is millimeter. Okay, then we have this matrix. It is going to be, let me use the calculator, 100 times 70 divided by 50. Okay, so it is 140 10 to power 3. Okay, then we have this, right? Now, so we got, this is our K1, all of this, and this is our K2, so we have to write. Okay, so let me just fetch all of each of the K1 and K2. Okay, this is K1, then we have K2. Okay, so here the K is plus this. Okay, so first of all 10 to power 3 and 10 to power 3 is common, so I will keep 10 to power 3. Okay, I will keep 10 to power 3 common here. This is 600 10 to power 3. Okay, right? It is like this. Okay, now I will multiply 600 to each. Okay, each coefficient. Okay, so K is going to be 10 to power 3 times 600, because 600 multiplied by 1 is 600, 600 multiplied by minus 1 is minus 600. Okay, so it is going to be 600 minus 600. Same here, 600 multiplied by minus 1 is minus 600, and 600 multiplied by 1 is 600. Okay, so we multiply each, because this is the rule of matrix. When there is a constant outside matrix, it gets multiplied to all the elements. Okay, so I multiplied it with all the elements, right? Plus, same thing I will do here. It is 140 minus 140 minus 140 and 140. Okay, so now we have the addition of these two matrices. Okay, now remember, I will show you some rule. Now let me tell you, I have also watched other YouTube tutorials from other tutors, and they have done this in a very boring way. Okay, because they have done like numbering 1 2 1 2 1 2 1 2. So we are not going to do all of these things. Okay, I will show you a simple way. Now for this we have to find the degree of the order of the global stiffness matrix. Okay, now order of global stiffness matrix. Okay, now the order of a global stiffness matrix, okay, K is total degree of freedom times total degree of freedom. Okay, so we have to find the total degree of freedom of all body, that is the order. Okay, then what we do, then of that order we will draw the matrix. Okay, global stiffness matrix. Okay, for example, if the degree of freedom is 3, then it is going to be 3 cross 3. Okay, then we will put all these elements here in a very simple way, not like what I watch from the other YouTube tutorials. Okay, I feel that it is confusing. So let me just first find the degree of freedom. Now how do we find the degree of freedom? Now degree of freedom is number of nodes times degree of freedom of each node. Okay, so number of nodes, how many nodes are here? 1, 2 and 3, right? We have total of 1, 2 and 3 nodes, right? One node is here, second node is here, and third node is here. So we have 3 nodes. And what is the degree of freedom of each node? Now in 1D, 1D problems, there is only 1 degree of freedom at each node. Why? Because as you can see here, the only possibility here is because each node can displace along only one axis. Okay, for example, if we look at these, the axial forces, the 5 kilonewton can cause the 3 to move to the right, for example. Okay, so it can like 5 kilonewton meter, because of 5 kilonewton, the node 3 is not going to move upwards, right? It is not. The only possibility it can move only in one direction, right? So similarly here, the 10 kilonewton will cause what? The maximum it can do is it can displace 2 to somewhere here, right? So there is only one motion possible, so that is along only one axis and centroidal axis. Okay, let us say this is x-axis, so the degree of freedom is only along the displacement along x-axis. Okay, so only one axis means 1. Okay, so degree of freedom of each is 1, so 3 times 1 is 3. Okay, so we got degree of freedom, we got the degree of freedom 3, so it is going to be 3 cross 3. Okay, so now we have to add them. Okay, so remember, I will show you few things. The last of first, okay, last element of first plus first element of second. Okay, now the last of first. Okay, now this is the last. Okay, this is the first stiffness matrix, and this is the last element and first element of second. Okay, so this is the first element of second stiffness matrix. Only they will add up and others will be as it is. Okay, as simple as that. Okay, now the other YouTubers have done like 1, 2, 3. We have 3 nodes, then 1, 2, 3, then this is 1 and 1. They will find where is 1. Okay, 1, 2, 1, 2. Then they will see where is 1 and 1. It is 600. Then they will place it here, and that is I feel like that is we don't need to do that. Okay, so what we will do, so we are going to do like this. Okay, so everything will be placed diagonally. Okay, we place everything diagonally. Okay, so first we will place this here. Okay, then we will place the second one here. Okay, now because of these two overlap, they will add up. Okay, so this and this will add up. Okay, so let me show it here. So here k is going to be something like this. Okay, first will be as it is, so let me copy and paste. This is going to be the first one. Okay, then I will place second one diagonally. Okay, but I will place the end one to the end. Okay, this one to the end. Okay, I will place it here. Okay, and then these two will add up. Now you can see they are coming close to each other, they are near, so the near will add up. Okay, so this will add up. Okay, now how much is 600 plus 140? 600 plus 100 is 700, and 700 plus 40 is 740. Okay, so all of this will be 740. Okay, and everything will be as it is. Okay, then where there is nothing, there will be a 0. Okay, so here it is going to be a 0, and here it is going to be a 0. Okay, so if I write it, it is like this. Okay, it is going to be like this. Okay, this is our stiffness matrix. Okay, simple. I hope you understand. Okay, I hope you understand this. If you have any doubts, you can comment. Okay, so this is our global stiffness matrix. Okay, so you can see these two are added here. Okay, 60 and 140 is 740. Okay, then all of others are here. Okay, everything is here. Okay, now we found the stiffness matrix, global stiffness matrix. Okay, now this is our step 2. Okay, now what is the step 3? Let me write step 3 here. Step 3 is formulation, use of stiffness equation. Okay, stiffness equation to find unknown displacements. Okay, so we always find this first. Okay, always. So unknown displacement we have to always find. Okay, at nodes. Okay, of course at nodes, because in finite element method we use what we see the displacement of the nodes. Okay, so what is the stiffness equation? Global stiffness equation is F is equal to K times U. Okay, F is the load matrix, K is the global stiffness matrix, and U is the displacement matrix. Okay, and I have told you in the previous class the order is what? Degree of freedom times 1, so it is 3 cross 1. The stiffness matrix is degree of freedom times degree of freedom, so it is 3 cross 3, and the order of displacement matrix is degree of freedom times 1. Okay, again I have already told you in the previous class, and this is the reason I always suggest you to please watch the video lectures in playlist. Okay, in sequence. Okay, because I tell each thing in each lecture, so you will find the link to the playlist in the description or also in the comments. Okay, so why is it is 3 cross 1? Because they are only on the nodes. Okay, force on the nodes and displacement on the nodes, because we have only 3 nodes, as you can see here, 1, 2 and 3 nodes. So it is F1, F2, F3 will be the load matrix, and U1, U2, U3 will be the displacement or U matrix. Okay, so here it is F1, F2, F3. Okay, and we have the K matrix, displacement matrix is here. Let me just copy it. Okay, but remember here it was also 10 to power 3 outside, remember, so I forgot to place here 10 to power 3. Okay, so it is 10 to power 3 times what? U, displacement matrix. Okay, so it is U1, U2 and U3, right? So this is our stiffness equation. Okay, now we have to apply step 4 is apply boundary conditions. Okay, boundary conditions, but remember with sign convention. Okay, with sign conventions. Okay, now let us see the boundary conditions. Now here we have U1 is 0 here, because this is a fixed support, right? So U1 is 0. Okay, then we have F2. Now let us suppose the forces to the right, they are positive, it means forces to the left is going to be negative. Okay, so minus 10 is at 10 kilonewton is negative, right? But it is at 2. Okay, so it is U2, right? So this is minus 10 kilonewton, so U2 is minus 10 kilonewton. Okay, not U2, 10 kilonewton is the force, right? So it is F2, right? So it is F2, but in the left direction, so it is negative. Okay, similarly F3 is 5 kilonewton, 5 kilonewton. What else do we have? We don't know F1, right? We don't know this F1, okay? But and U1 is 0, okay? So these are our end conditions, right? So I will use them in our stiffness matrix equation, okay? So here it is. So I will copy all of this and substitute the end conditions, right? So F1 it is unknown, F2 is minus 10, right? Minus 10 kilonewton, and F3 is 5 kilonewton, right, as shown here, and this U1 is 0, okay? So this is our global stiffness equation along with the boundary condition, okay? Now with the help of this we can find U2, U3 first, okay, and we will then find F1, okay? So step 4, find unknown displacements, okay? Displacement U2 and U3. Why not U1? U1 is already 0, okay? We know it, right? So let us apply, let me draw it here. So now let us apply elimination method, okay? So because it is the multiplication of these two, right? So this element is 0, so this is the first element, right? So because of first element, the first row, okay, and the first column will cancel out, okay? Sorry, not this, the first row and the first column, okay? So they will cancel out, right? If it was U2, if U2 was 0, then this is second, right? So second row, second element. If U3 was 0, then it was, because it is the third element, then third row, third column. Because 0 is the first element, so first row, first column, okay? So I cancel out first row, this is first row, this is second row, this is third row. So I cancel out first row and column, first column, second column, third column, and this is the first column. So first element is 0, first row and first column is out, okay? So we will get some simplified, right? So what is our simplified matrix stiffness equation? Minus 10 kilonewton, because F1 is out, right, and it is 5 kilonewton here, then it is 10 to power 3. Here is only these three things, right? So why not just copy them, okay? I will put them here, and here you have U2 and U3, okay? Now what? Now it is, how many unknowns do we have? U2, U3, right? So we have two unknowns, right? Two unknowns, it means we need two equations, right? If we have two equations, we can solve the system of linear equations, because they are linear equations, to find the two unknowns, okay? So we will use system of linear equations with two unknowns to find the two unknowns, okay? So we will formulate the first equation, then second equation, okay? So the first equation is going to be minus 10 kilonewton is equal to 10 to power 3 times, now first row times second column, first row times this column, okay, 740 times U2 minus 140 times U3. Oh, I am sorry for being fast. So first row, I have to multiply this row with this column, right? So 740 times U2, first element, then minus 140 is the second element, and U3 is the second element, no, right? So second element multiplied by second element, first element multiplied by first element, because here is minus, so 140 times U3 is the second element times second element, okay? So if we rearrange this, now see here it is kilonewton, okay? So why not write this? I will write kilonewton, I will put the kilo outside, okay? So here it is only Newton and Newton. Now K is 10 to power 3, okay, and 10 to power 3 and 10 to power 3 will cancel out. Okay, so this is not here. Okay, so it is 10 Newton is equal to this, right? So let me put it in standard form. Ax plus bx equal to c. Okay, then we have a2x plus b2x equal to c2. Okay, these are, we will put them in this standard form. Okay, so let us say u2 is x and u3 is y. Okay, so 740 u2 minus 140 u3 is equal to minus 10. Okay, this is our first equation. Then let us write the second equation. Second equation is going to be what? 5 Newton is equal to, second equation is from here, right? So this row into this column, right? Minus 140 times u2 plus 140 times u3. Okay, second row times this column, right? Because in the first equation we use first row, in the second equation we will use second row. Okay, so it is minus 140 u2 plus 140 u3. Okay, now let us put it in the standard form. So minus 140 u2 plus 140 u3 equal to 5, right? This is our second equation. Okay, so let us call this as u2 as x and u3 as y. Okay, it is not x, it is y, right? Because why x and y? Because we have to use system of linear equations with two variables, right? Because we have u1 and u2 and u3, two unknowns. So x and y, they are two unknowns. Okay, so we have to use the system of linear equations with two unknowns. Okay, so let me use a calculator. Solve system equations, two unknowns. Okay, so let me put the values. Okay, so x I will put 740, and at b I will put minus 140, and at c I will put minus 10. Okay, then at coefficient of x is minus 140 because u2 is x, and then coefficient of u3 is y, so coefficient of y is 140, and c2 is 5. Okay, and c1 was minus 10. Okay, so when I solve this equation, what I get? I got ux as, which is u2, which is, I got it as 0.0083. okay, but it is in mm. Okay, and then I got y as 0.0274 mm. Okay, so here we found the u2 and u3. Okay, so now let us move on. Now since we found the unknown u2, okay, because we first have to find the displacements, then we will find the unknown force. Okay, now the unknown force is what? F1. Okay, so I can find F1 from this equation. Okay, because F1 is the first element, so we will need this first row and this column. Okay, from here or here, anywhere. Okay, so let us, we have to find F1, right? So we will use this, all of this. Okay, for F1, if we need to find this element, then we will use all of this. Okay, the second row and this whole column, so we will use all of this. So from here I will get F1 to be 10 to power 3 this first row times this column. Now 600 times 0 is 0, so I will not write. Minus 600 into u2 plus 0 times u3, so I will not write that. Okay, so F1 is this, right? So okay, so it was basically step what? Step 5, right? Step 5 was what? Find unknown forces, and also remember one thing, we have to check using equations of equilibrium. Okay, equations of equilibrium. Okay, I will tell you in a moment what it is. So now what is the value of u2? It is minus 0.0083. Okay, so it is 10 to power 3 times minus 600 times negative 0.0083, right? It is this, right? So negative and negative is positive, so it is 10 to power 3 times 600 times 0.0083 kilonewton. Okay, so how much is it? 10 to power 3 is 1000 times 600 times 0.0083, right? So we got, it is in Newton, right? Not kilonewton, because 10 to power 3 is here. So it is 4980 Newton, right? So it is 4.98 kilonewton. Okay, so we got F1 as 4.98 kilonewton. But what is F1? Let us see here. F1 is here. Okay, this is F1. So F1 is the force at this fixed end, and the force at fixed end is, it is only possible, I mean it is a support reaction. Okay, so F1 is a support reaction. So we got a support reaction. Let us say it is R. Okay, let us say the support reaction is R, and we got R as F1, which is 4.99, right? 4.98 or something. Where is it? Yes, so our support reaction is this, right? So now we have to check. Okay, we have to check. Remember, this is very important, using equations of equilibrium. Okay, so now what are equilibrium equations? I have made a lectures. Okay, and so equations of equilibrium are summation of f of x equal to 0, y equal to 0, and z equal to 0, and summation of moment along about x axis, y axis, and z axis is 0. Okay, so we have 6 equations of equilibrium. Okay, now which one do we apply here? Because the moment doesn't exist in actual. Okay, so it doesn't exist, so we will not apply this. Now we don't have to apply summation of forces about y axis or z axis. Why? Because the forces are only acting along the x axis. Okay, in the 1D meshing, so we will only apply summation of f of x equal to 0. Okay, so we will apply this. So this is, let us this, right? So r minus 10, because 10 is to the left, so it is negative 10 plus 5 equal to 0. Okay, so from here I get r to be minus 5 plus 10, which is 5, right? 5 kilonewton. Okay, so from the equations of equilibrium, this we got 5, right? So F1 is 5. Okay, so let us see. So we got it, this is from the finite element method, and we got R equal to F1 equal to 5 kilonewton, right? From what? From equations of equilibrium, right? So why do we get different values? But the thing is that 4.98 is highly close, right? It is approximately equal to 5 kilonewton. Okay, so what is the check? Check is about, if we have to see if they are approximately equal. Okay, since they are approximately equal, it means our analysis is good. Okay, now if somehow if we had got this value using FEM as, for example, 2.5 or something, and it was no way equal to what we get from the 5 kilonewton, right? Then what we do, it means something is wrong, we have done poor meshing. Okay, then we would repeat all the steps, okay, until we get 2.5 close to 5. Okay, that process is called convergence. Okay, so we have to see if we need convergence. Okay, so we have to refine the mesh until we get the convergence. Convergence means we got a value which is very much close to the actual. Okay, so here 4.98, which is approximately equal to 5 kilonewton, it means our meshing is very good. Okay, so we don't have to repeat the steps. Okay, so that's it. If you have any doubts, you can comment. Okay, and see you in the next class. Thank you.